Earth is moving on its axis, and that causes a real unique effect called the Coriolis motion. And that happens in both the atmosphere and in the oceans. Now, another big effect that we have is the solar radiation. That's the sun shining down. And that gives us big temperature differences between the land and the water and the air. Okay, so those are two big things, Earth motion and the solar radiation. Now in our ocean, again, the hydrosphere, that's the whole envelope of the water. As you see that Earth planet spinning around, that's the oceans, as well as the fresh water. We don't want to forget the fresh water. We only have 1% of it, but that's the important part that we need. And our atmosphere is the envelope of air. And again, the way they act together, the way they interact, the oceans and the atmosphere, is what creates our weather. Now, if you look at this picture, that is a pretty daunting look at an ocean. As you look at this picture, an early scientist would try to figure out what is happening here. What is making this move? Why are there dark parts? Why are there light parts? What's making it go up and down? We know those to be currents and waves, but what is causing those? And again, if all that's moving at the surface of the ocean, the water, what's going on in the atmosphere right above it? Is it moving the same way, or is it moving a little different? People had to deal with the oceans and the atmosphere for a very long time in history without understanding the true science behind it. So again, our scientific studies, as they evolve, we learn more about our Earth's movements. And again, through scientific observation and recording those observations is how we make a little bit of progress. Now, when you first look at these big pictures these are tornadoes. Tornadoes are a pressure system that happens over land, and the air is, see, it's swirling. If you look at that picture to the right, you see there's things flying in the air. Why is it flying in the air? What is going on? Why is the cloud so dark? Is it all attached to the ground? Why is it spinning? Why is it rotating like that? And then look at the other big cloud picture, the tornado. That is a huge storm. Why is it so big? So again, when we look at these things, we not only just have to know that they're there and what to do and how to act with them, since they are a hazard that we have to deal with, but what is the science behind them? How do they work? Now, this is a hurricane. Hurricane is a storm that develops over ocean water. It picks up a lot of moisture there, and then sometimes it can come over land. Usually when it hits land, it starts to burn out most of its energy, so it starts to slow down. But here you see on the lower left, this is a picture of the hurricane coming in on Hurricane Wilma down in Miami. And if you look, look at how it's coming in. You see the eye of the hurricane, and then you've got those spiral arms. Why are there spiraled arms? Why are they spinning? And what is the eye doing there? Again, and look at how the trees are affected. So how does the science make these hurricanes, these storms happen? And how can we protect ourselves from them? Now, another name for a hurricane is also a cyclone. You also might call it a monsoon. Look off of the coast of India here on the right picture. This is a cyclone from 2013. Again, the storm develops over the ocean as it picks up speed, velocity, and moisture. Then once it hits the continent, then again, you can see the damage that it can do. Look at all the water that it is dumping down, all the wind. So again, our oceans and our atmospheres work very close together. Now, our picture in the middle, that is a water spout. Now, I live in North Carolina, and I live next to a big lake. And our lake, we do have these water spouts when we have big thunderstorms. So the water spouts can happen anywhere, but they have that same twisting as the hurricanes and the tornadoes. How can that be with all water instead of just air? All right, so we've had a lot of scientists in the past that, again, have started describing their observations and recording them. One of the great scientists of the past was Ben Franklin. And you guys may know him for a lot of different things in history. He was kind of all over the place. But he was one of the first scientists that actually started recording and made a record of the Gulf Stream. And that's out in the ocean. So you see, Ben Franklin, he was going back and forth between Europe and England and France and the colonies. He made about 8 trips going back and forth. And as he was going, he knew that the sailors knew that if they could catch the right currents in the ocean, that their trip would be very fast, but they didn't always get those currents. So he was trying to figure out, where are these currents? What's going on? He started dropping thermometers into the ocean to take the temperatures. Sure enough, he discovered there was warmer water. When they hit that warmer water, that was the current that was then called the Gulf Stream, because the water was coming from the Gulf down in Florida, the Gulf of Mexico, all the way up, and would take them right into Europe and England. Now, that same Gulf Stream is part of what keeps England so warm, because as far as when you look at them on the map, England should be colder, but it's that Gulf Stream. And again, Ben Franklin was one of the first people to record this. And this is actually a map that he recorded. And if you look at some of the funny things that are on it down on the bottom right, this is a chart of the Gulf Stream with some cool pictures, look like a mermaid down there. So again, these old maps and all are fun to look at. But it does record years of these temperature observations, is how it all came to be that he got this map and created it. Now, he also did a lot of recording of his thoughts and in writing in books, and these are called his weather lores. So one thing that he recorded that was funny was about the ring around the moon. And I don't know if you guys have ever looked up at the moon at night, and these pictures are kind of showing you how it looks like there's a ring all around the moon. Now, Ben Franklin figured out that that usually meant that there was rain that was coming. And the halo that was around the moon is caused by the refraction of the moonlight. Well, how can you get refraction of moonlight? Well, you can if the clouds are so high up that those water molecules are starting to crystallize into ice. So again, those cirrus clouds that you see there that are the long, skinny clouds, those are very high up in our altitude, in our atmosphere. And so those were, again, creating those ice crystals. So we have a lot of weather lore that we have. Have you guys ever heard of the story about the April showers brings May flowers? Or red sky at night is red sky at night, sailors take warning. Red sky at day, sailors delight. Okay, so there's all different kinds of weather lores. Now, again, one of the big principles we want to talk about today is this movement or motion. Our planet is a unique planet in that it is spinning on its axis. So it's rotating, giving us day and night. And it's got the bigger revolution going around the sun, which is making that revolution. Big name, big motion. Okay, so we've got rotation and revolution. So that creates a weird things happen on our planet. Because if you were standing at the North Pole and somebody was standing at the equator and then somebody was at the South Pole, would you all be moving at the same time? No, the equator would be running very fast. So that puts a lot of stress on our planet. If you think about the rocks, the lithosphere that's underneath, the water, and then the atmosphere, it's all going to be moving a little different. So our forces are pulling away and also pulling back through with our gravity. Now, we had a lot of early astronomers that led the way in some of these discoveries. You may have heard of Galileo, Newton, Kepler, and many, many more. We had to build on the discoveries of these scientists to get to where we are now. Now, our oceans and air are due to these forces. Now, as you watch this video go, you are looking at the Earth with the North America's on the top left. You see Florida. South America is kind of straight in front of us. Now, that green that you see going, these patterns, you see how they're kind of going from the Gulf Coast of Mexico, the Gulf of Mexico, all the way up, all the way over to Europe. So this motion is what happens by these forces. So some of these forces I'm talking about, when you take a physics class, you will learn a lot more about this. But this is a little toy that helps us show the centripetal and centrifugal forces. So let's go ahead and watch. Phoebe?
Into this top edge without it falling down. And now, what happens if we stop?
Uh-oh. So what happened there? Let me see if I can get it to play one more time.
Make this ball come to this top edge without it falling down. And now, what happens if we stop?
All right, So the motion that Phoebe was able to generate, that motion was actually creating a force. That force we call the centripetal or centrifugal forces. And these forces are actually what helps keep our oceans and our atmospheres from floating away. Once it goes in that circle, it creates again its own force. Now, we don't have many of these little merry-go-rounds on our playgrounds anymore, but if you have anything that's spinny kind of like this is a fun activity you can do. Now, you watch how she's spinning, and she lets the ball go, and then it comes right back around to her. Now, this is, again, kind of hard to understand, and again, you'll learn more about it in a physics class, but because of the rotation that she's doing, the revolution, because she's moving in that circle changes the path of the ball. Now, if you look to the picture on the left, the red mark is the ball. When she lets it go, it's going in a straight line. That ball is moving in a straight line. But because of the motion of the circle there that she's going, the motion, that it looks like it's bending. Okay, remember this funny picture because we're going to get more into this in a minute about what these forces do to both our oceans and our atmosphere. All right, so this Coriolis effect, that idea that motion creates a bending, creates a movement, a force. So this rotation on our axis is what creates that, and it affects both the oceans and the atmosphere. Now, if you look to the picture on the far left, top left, you'll see our little planet, and you've got, this is looking at the motion and how it affects the atmosphere. So you see we've got all these different kind of circles going up and down because warm air rises, cold air sinks, warm air rises, cold air sinks. But you also have another effect again with this Coriolis effect because of we're spinning, it makes everything move, kind of bend funny. Now, looking at the atmosphere, again, you see this big long line that's down at the bottom. Okay, that is the jet stream. And again, you can see how it's dropped way down like over you guys right now, and then goes back up and loops around. So we have these big, all of this motion affects these really big features of our climate. All right, now the last picture I want you to look at is on the bottom right. And if you look at this, this is showing you the currents in the ocean. Now, if you can follow some of these little arrows, the middle of the map you can assume is the equator, right? If you can find California, see if you guys can recognize your land features, look for North America and South America, and then you find California. Your water currents are coming down from Alaska. They're coming down and then going around. So your water, when it comes down, if you've never gone to your beaches, your water is cold. It's very cold. All right. But as you watch those arrows as it goes down, see how it goes and it loops around. So the water is going clockwise. Now look below, look to South America, right off the coast of Peru, kind of where the South America does that. And you see those same arrows, but it's going the opposite way. So in the northern hemisphere, this Coriolis effect makes the currents in both the oceans and the atmosphere go clockwise. And in the southern hemisphere, it goes counterclockwise. All right. Next time you go to flush your toilet, notice which way the water swirls. All right. It affects everything. All right. If you're also looking at this map, if you look back to when we were talking about Ben Franklin, if you can find the east coast of North America, remember I talked about the Gulf Stream in the ocean, how it's flowing up from the Gulf of Mexico and all the way around. Can you find that? That's how Europe again was able to stay so warm. And then it circles back around doing clockwise. All right, so that's the Coriolis effect. Now, all of this comes into play when we have all the different motions and we've got all these different temperatures and we've got land and water that's getting heated up and cooling and moving. That creates a lot of kind of chaos that we're going to try to make sense of. All right, so as you again watch this planet spin around, you see the land features, and then again those hydrosphere, the ocean features. And once the atmosphere kind of gets over the land surfaces, that hot and cold air kind of has to fight over each other. They have to they're able to push each other out. So temperature and density kind of go together. But as we track all these systems of the temperatures, this helps us predict our weather. Now, how do you know if something's hot or cold? You have to use tools because it's all relative. Temperature, again, is going to control our density. All right, so warm is going to be less dense. It's going to float. Colder is going to be more dense, and it's going to be heavier. All right, so we also have one of our driving forces is this solar radiation. Now, of course, as our planet, again, is rotating and revolving, the sun shining in on us. So again, wherever that hits, the sun's radiation hits, the most intense is usually going to be around that equator. And you see, again, how it tilts, makes our different seasons. Now, if we did not have this Coriolis effect, this motion that keeps us spinning, and it creates those centrifugal and centripetal forces, we wouldn't have an atmosphere and we wouldn't have oceans. Okay? You can study other planets in our solar system and see those that do not have atmospheres, and they don't have that water that's available. So again, that motion and the heat plays together. All right, this is a map I want you to look at. First of all, look at the key. So the blue colors, the purple to blue is 0 degrees Celsius or 32 degrees Fahrenheit. Orange temperatures are going to be your higher temperatures. Now, as you look at this map, again, can you find California? Can you figure out where you would be? And then can you figure out where I am in North Carolina? If you can find Florida, I'm about halfway up. So as you look at these different months, as the time passes, we're looking at the surface temperature, the atmospheric variations. So like 50 to 100 feet up in the air. Can you tell where you would want to be if you wanted to live somewhere hot all year long? Can you pick on the planet where you'd want to live? Or opposite, if you wanted to live somewhere where it was cooler most of the year, or what we call temperate. So again, it is collecting this data that's very important. Collecting it over time, again, allows us to predict what will happen. All right, here's an experiment with Phoebe. I'll let her explain what we're going to do with reading a thermometer.
Thermometers like these two are really important for collecting data about temperature, how hot or cold something is. So for this experiment here, we have 2 containers with 2 thermometers, one with dark sand and one with light sand. So you want to make sure the thermometer is underneath the sand and then place them outside where the sun is shining directly on them. So you want to see where the light is coming from and make sure that the thermometers are right there. And then we're going to come back and check the temperature and see if there's any difference between the 2 sand colors.
Okay, so you may have some thermometers at home or you may have some at school. Again, they make all different kinds of thermometers depending on the purpose. So because we're not using anything that's super hot, we were using these little plastic backed ones, but you still have to be careful because there is glass. Now, the red material that's in the thermometer is no longer mercury. That is an alcohol kind of mix that's going to make that red part that goes up. All right, so you've got your experiment going here with your dark sand and your light sand. After 20 minutes, I want you to go ahead and make your guess. What do you think will happen? Make your prediction. It's not right, it's not wrong, it's just your guess. All right, 20 minutes later, the dark sand is sitting at right about 40 degrees centigrade. It's about 105 or so Fahrenheit. The light sand is only at about 70 degrees Fahrenheit. So the darker sand absorbs more of the sun's radiation. It absorbs more, contains more of the heat. The lighter color releases or it reflects the radiation. All right. So now that you've done this experiment, if you were going to go out on a hot day and you didn't want to be all hot and sweaty all day, would you wear dark polyester or would you wear lighter linen clothes? Okay, all of this goes together. If you live in a hot climate, would you paint your house black or would you paint it white? Okay, so again, all of this affects. So you can do this experiment with just light sand and dark, and the light sand and dark sand. You could also add in some water, just plain water, and also some salt water, and see what kind of temperatures you get. All right, another important science idea is this idea of density. Now, when we're talking density, when it comes to oceans and atmosphere, density and temperature are kind of go together. Okay, so this is Phoebe. She's going to tell us a little bit about this density.
When we flip this, why does the green fluid fall down?
Now, this density timer that we have here, usually this green fluid is a kerosene. It's a heavy liquid. Again, it's heavy in weight. It's denser. It's got more density, so it's going to come down. The other is probably some kind of oil, mineral oil probably, that's going to rise back up. Now, you can do this experiment at home too. You can look around just in your kitchen. A lot of salad dressings, like the oil and vinegars, those you can see as they separate. Even things like peanut butter. Well, also the solids, the dense part comes down, and then the lighter oils float to the top. Okay, so there's all kinds of observations that you can make for density. All right, now here's where the density kind of and the temperature work together. Look at number 1. Underneath this glass is a candle. That's what you can't see. See a little bit of the flame of the candle. So this denser liquid that's in the bottom, once it gets the heat, once it starts warming up, it then begins to become less dense and floats more towards the top. Look at number 3. See, this is a little spiral. This is another something simple you can do. The spiral is spinning. Why is it spinning? There's just a candle underneath there. With the candle, there's a column of heat. As that heat comes up, again, it's moving that air column and is allowing that spiral paper to move. Now, we even have this idea of density and convection at the lithosphere, the layers of rock that we have. Picture number 2 is looking inside the surface of our planet. So the very top crust of our planet, the lithosphere, underneath, and you have the mantles and all underneath. But you see how coming from the inside the planet, super hot. There's hydrogen and oxygen fused down deep in the bottom. And as it's coming up, it's outgassed as steam. That's actually where our water comes from. Now, not all of that gets to escape as lava and other products. Sometimes it comes back down as it gets away from the heat source, it cools and it sinks. So again, it rises. When it cools, it sinks. All right, so again, this is the idea of that density and temperature. All right, so here's a trick. Density, salt water to fresh water. And these are, again, experiments that you can do at home. All we're looking at is that fresh water is less dense, it's lighter than salt water. And salt water that is cold is very dense and it goes to the bottom. Cold water sinks, warm water rises. So the warm salt water is less dense, it rises to the top. Again, looking at the different layers. If you look to the far right, you see how those 2 layers do not mix. What happens on the one in the middle though? Can you guess which container has the warm water? And where, and why it's going up. Again, idea of density and temperature. So again, that warm water is going to rise up and displace the other. All right, now looking at our atmosphere, the atmosphere is the envelope of air that's all around our Earth. And this is a kind of picture demonstrating as it goes, these little meteors are coming in, hitting different layers of the atmosphere. Now, as you go out into the atmosphere, there's not these like strong divisions. It's not like a little road sign that says, you're now entering the thermosphere. But again, we can collect data and information. So the one that we are most concerned with, of course, is the troposphere. If you look to the picture on the right, the troposphere is where we live. That's where all our clouds are. That's where 99% of the water vapor is on our planet. So again, the troposphere is this lowest part. We see the clouds moving and all, again, back to our rotational revolution. As you go up through the different layers, each layer has kind of a different role to do. Now you get the stratosphere and the mesosphere. Mesosphere is where you have a lot of the aurora borealis, or the northern lights. A lot of the ions are happening there. The Kármán line is sometimes referred to as kind of the end of space, but then you also have your thermosphere, exosphere. So will you find clouds? Will you find clouds way up in the mesosphere? No, only in this bottom troposphere, okay? Again, different layers, different functions. Now, when we look at our atmosphere, again, the composition of the atmosphere changes with the distance from the surface of the Earth. The temperature is changing. Some of you may be familiar, if you've ever traveled and gone to the city of Denver, Colorado. When you go up there, it's the mile-high city. It's very high in elevation. It's not as easy to breathe there. When you go higher up in the elevation of our troposphere, there's less oxygen. So if you see down here on Mount Everest, there's a little Mount Everest on the right. If you were to climb to the Mount Everest, to the top, is there oxygen to breathe? Have you ever watched any of those expeditions? You have to bring oxygen with you. So again, as you go up, that's where our temperature begins to fall as you go higher up in elevation. As you continue to go up, if you look at the temperature as you go up through the stratosphere, pretty constant temperature. Get to the mesosphere, the temperature falls, it drops. But then look at the ionosphere, the temperature goes back up. Well, that's kind of weird, isn't it? Down, up, all of this motion again, moving, is caused by different effects. Now, as you go up to the ionosphere, those different layers again have different roles. So they're collecting a lot of the radiation that's coming from the sun, different parts. So again, we have all these different layers. There's not a clear line. They're kind of changing a lot. And again, as you look through our atmosphere, what we are mostly breathing is nitrogen. And of course, we need the important oxygen. And of course, our plants and all need the carbon dioxide and hopefully give us the oxygen. So again, we've got everything is changing, okay? All right, so again, this is a cool picture that shows, again, kind of the troposphere. This is looking kind of at an angle. And again, the stratosphere up above. So a lot of times when we're doing like our rocket launches and stuff and going out, again, the only part that has clouds, that has the weather, is this lowest part, the troposphere. Now, I mentioned earlier the sun's radiation. If you look to the left, these diagrams show you a little bit of how the radiation is reflected and absorbed. Now, remember our experiment we did with the dark soil and the light soil? Okay, as you remember these, so different layers are going to absorb different features. Some of it is reflected back. Some of it is released. That is the important part of our atmosphere. All right, you have an experiment to do here. This is activity teachers. You find these worksheets the same place that you registered, and I believe it was also sent on the link to join today. But there are 2 sheets, and I'll go ahead and let this play.
All right. Okay. In today's activity, you've got 2 worksheets that your teacher will give you. One has the Earth, one has 2 small quarter sections. Once you get those, you can start coloring them up. Here you see I've already colored some. Now after you've colored them, you're going to get started with this one sheet here. All you're going to do is use a pair of scissors and just cut right here at this one side, and then cut along this one edge here, and see this dotted line, so that you will get one flap that goes all the way up. All right, everything else is still intact. Once that's in place, you can use your glue, dab down a couple of the different corners. Now these cross sections that you cut out earlier, one is the core. Again, just put a little glue, and the core is going to go on the bottom. And again, here's a reference for your division of the upper and the crust. And then we've also got our atmosphere. Put a little glue, again towards the middle core, the troposphere. That's the part, again, where we live, where our weather happens. So now we've got a nice diagram that will fold down and show the Earth and the different oceans, as well as folding up to looking at the division of the crust and the upper mantle and the divisions of the Earth's atmosphere.
Okay, hopefully that makes sense. Again, you can see on your original piece, there's a little line that says to cut into it. The other piece you just fold up. All right, now regarding the lithosphere, the inside part, the rock part of our planet, we now, on our diagram, we've got 4 divisions, but we think there's another one, and there may be a 5th one. So the solid inner core, again, we believe to be more solid because of the way the seismic waves go through it. The waves act very differently. So again, there may now be 5 layers, with the solid core being a liquid nickel, and iron and cobalt. All right, so again, looking down at the reference information as far as the lithosphere, again, the hot, less dense rises, cooler sinks. So you get that convection current that's going, again, our rotation and revolution. And then you've also got additional information for your atmosphere, the divisions of the atmosphere and those different temperatures. And again, the back sheet of paper can just be a plain white sheet of paper or scrap paper. That's up to you. All right, another thing you can do on this is also label your different continents and your different oceans and look at those key characteristics of those oceans. All right, so now when we're talking again about the water cycle, the interaction of the oceans and the atmosphere, a lot of times we leave it just oceans, atmosphere, but we're really talking about the whole hydrosphere, all of the water. So most of you are familiar with the water cycle that shows you on the right, where our ocean waters evaporate. Now, when things evaporate from the ocean, when our ocean water evaporates, is it fresh water or salt water? If you've never done that, ask if you can boil some salty water on your stove at home. Okay, that's a fun experiment. And then we've got our rain that precipitates, again, our rivers. So we'd look at all of the water that we have on our planet. That's the water vapor, the available flowing water, water that's in the ice caps. All of our water, our fresh drinkable water is only 3%. And even out of that fresh drinkable water, 2% is frozen up in those glaciers that we can't get to. So really out of all of the water we have on our planet, only 1% is available water that's tapped down in our underneath the ground and again, flowing rivers. Now, the whole time that this water is flowing from the high tributaries of the mountains, flowing over the different rivers, it's going through, it's always flowing over those rocks, right? One of the unique components of water is that it has that strong bond. It can break things apart. So as it's flowing over those rocks, it's taking some different minerals with it. And that's how your salt ends up in the ocean. Okay, and when salt water evaporates, it leaves the salt behind and it's only fresh water that you get. All right, so again, unique thing about water is that here on our planet, our water exists naturally, solids, liquids, and gases. If you look at a periodic table that shows you the solids, liquids, and gases, look up how many other liquids that exist naturally here on our planet. There aren't many. So again, water is very unique. All right, so if you look at this little pie diagram, again, it's showing you the fresh water, 3%, most of the planet, 97%, salt water. All right, so let's look a little bit closer at our oceans. So this is a great map that shows us all the different kind of the motions that are in the oceans. Again, cold and warm. You can see the warm words or the warm arrows are carrying the warm water. Cold or the blue, it's colder waters. So as you look at this stuff cycle around, remember that Coriolis effect I talked about? Remember the people that were on the, when Phoebe did the ball trick and the people that were on the twirling, given the ball, and it was going in the motion? Okay, so when you get that, again, you get the northern hemisphere, you've got going in the clockwise direction. Southern hemisphere, it's counterclockwise. Again, meets at the equator. So if you are sitting out in the ocean in the middle of that equator, where you've got these big currents that are all coming together, that's a little scary, huh? There's a lot of things going on, a lot of motion. And again, how does our warm water become cold water? How does the cold water become warm water? So that's what we're going to, again, look at. All right, this is again a picture of that surface ocean currents. We had this before, but now that you've studied a little bit more about the currents and the way they move, I want you to kind of watch what's happening here. Can you follow the different motions? Now, again, things are always changing. So this is just kind of a blip in time of what this motion would have looked like. Again, always changing because our planet is doing that rotation and revolution. And again, a mixture between those lighter, less dense atmospheric and the heavier, more dense liquid oceans. All right, so now look at this surface current. Now this is kind of cool. If you look at the date stamps, so this is August, September. Okay, August through September. So this is showing, look at all those little swirls and curls. Now remember Ben Franklin trying to get home back to England and go back and forth? So this is that Gulf current that he was able to get, comes from the Gulf of Mexico, you see coming up and around. But look at all those eddies, and can you imagine traveling way back then? If you didn't know all this information about the currents, you can see how it would be easy to get a little lost, right? And that did happen to a lot of explorers. So again, you look at all these curls, all this rotation that's happening, all these different currents. So if you have these surface currents happening on the ocean, and you have these currents that are also happening in the atmosphere, that gets a little chaotic. All right, so now look at this picture for just a second. Now this is showing you again, those surface, the atmospheric currents. So our water's doing one thing. Is our atmosphere doing the exact same thing? No, it's a little different. Again, they're all affected by that rotation, the motions. But again, the densities and temperatures come into play here. So again, what scientists have to do is do our best to kind of put names to describe it, to put numbers to it, to best describe as much as we can, because then that way, just like your activity you have, that's a way of putting it all down in writing. So now you have a basis to be able to talk to somebody else about something that you have seen or discovered. Okay, so you have to be able to describe it to be able to share it. All right, so why are our oceans important? We know that they're home to many of the organisms, controls our weather patterns, and again, our global climate patterns. And we're going to talk about more about that on our next class. But again, our oceans, most of our planet is ocean, right? So again, 97% of the Earth's water is this salt water, and it covers 70% of our planet. And even though those numbers are big, we don't know a lot about the ocean. It's still pretty new science that we are just discovering. All right, so along with this motion that we've been talking about is this global conveyor belt. Now, if you started as a small little drop of water and you started up there, see where the start is, up at the top at Greenland, and you were super cold and you were very salty, that area is super salty. And as it's cold, salty water, it's heavy, so it sinks, right? And follow the trail that it takes, those bottom currents. Then it goes all the way over, eventually starts to get a little lighter, mixes in, it's not as dense as it used to be. Now it becomes surface traveler, and again, can break off in different ways. But you see this whole path. This takes about 1,000 years to complete this whole conveyor belt pathway. That's a long time. So there's a lot of different things happening. If you stand in the main part of these currents, they're pretty steady, but what happens along the edges? And is it just this one path, or are there little side roads? Probably a lot of side roads. All right, let me show you another picture of this conveyor belt. Now this conveyor belt, this is showing you a picture of the map without the water surface that you can see, but now you can see down to the ocean bottom. Okay, this is called bathymetry, where you map the bottom of the ocean. And there's only about 20% of the ocean bottom that's been mapped. So again, we don't know a lot about it. We're still learning. But again, it starts up in Greenland, cold, dense water, comes up. Eventually, it loses some of that salinity, becomes less dense, becomes warmer, and then continues on. So as you look at these different pictures, there are a few problems. You see how the masses of the water have to move. Well, you've got the big Pacific Ocean. That's a huge amount of water. And then you've got a smaller bit there at the Indian Ocean. So there's a lot of different things happening here. again, motion, the big thing that is influencing this motion. All right, now as our water is moving along, if it happens to hit a big rift in the bottom of the ocean or it hits a continent, what happens? So when we look at this, it's called upwelling. So this is one way that that cold, dense, very heavy salted water can get up to the surface. And once it gets up to the surface, then it's going to warm up and it'll be able to change. All right, so this is called upwelling. Now, if we go back to this picture, you see all along like the Arctic down at the bottom, there's not a lot of places for that water to run into, right? But if you're in the middle of, and you hit another continent or if you hit a big continental ridge, then that's going to be an issue. All right, so we have a lot of upwelling. Right around the California coast is where we have, again, a lot of upwelling. All right, look at this picture. This is just a plain old picture of the map of the Earth. You can see if you can identify the continents and see if you can identify the oceans. Now, this is, again, where it's just a way of us trying to get information together to be able to share it. On a map, it's real easy to kind of put a line and say that that is the Arctic Ocean. But again, there's not, it's kind of hard to tell. You gotta, it's always going to change a little bit. All right, so as you're looking at this, if you look off the coast of California, okay, there's ocean, and then you look below it, there's ocean. It's easy enough. You look at the United States, North America, then there's South America, land to land, okay? Looking off the coast of the United States, there's water, there's ocean, and there's ocean, okay? We've got Europe, that's land, and Africa, land. Makes sense. Here's the problem. India, land, water. That's a problem. Then we go further over to Russia, Japan, that's land, and Australia, land. So that difference between having the land to water and the water to water, land to land, the way that those surfaces heat up, remember your experiment you did earlier, that creates a problem and an issue. So we have something called El Nino that we do believe started kind of in this area here of the Indian Ocean. And it's a phenomenon that happens. Early Peruvian fishermen knew all about it back in the 1400s because they were big into collecting their sardines and their anchovies. And they realized that the temperature warmed up and it changed kind of right around Christmas. So that's where the El Nino comes from. But then some years it didn't. So again, we have learned more about this effect. And we also know that it is a La Nino and an El Nino. So here we go a little bit about these.
Warmer or colder than average ocean temperatures in one part of the world can influence weather around the globe. Boggles the mind, right? Here's how it works. During normal conditions, trade winds, which blow from east to west, push warm surface waters towards Asia, piling it up in the western Pacific. In some years, though, the trade winds weaken. The warm surface water moves eastward and reduces upwelling of cold water off the coast of South America. Climatologists call this El Nino. Its climate impacts show up mostly in the wintertime over North America. The warmer ocean fuels an intensification and southward shift of the jet stream. This brings flooding to the southern United States and warmer, drier conditions over parts of the Pacific Northwest, northern U.S., and Canada. But eventually, those trade winds pick up again and sometimes become even stronger than normal. When that happens, they blow the warm water back into the western Pacific and restart the upwelling of cool water towards the surface in the eastern Pacific. These strong trade winds are a signature of what is called La Nina, unusually cold conditions in the tropical Pacific that displace the jet stream northward. La Nina can lead to drought in the southern U.S. and cooler temperatures, heavy rains, and flooding in the Pacific Northwest. El Nino and La Nina together are part of a cycle that influences extreme weather and can impact food production, water supply, and even human health, not just in the U.S., but in many parts of the globe.
Now again, because we are a closed system, what happens in one part of the world is going to happen in the other end, but its amount or how the effect it has might be a little bit different. All right, so let's go ahead and let's talk more about what makes the weather. Now we look at the picture. Luckily in California, everybody needs to California to the weather. You guys don't usually have a lot of these big storms. Now in North Carolina, we do have a lot of tornadoes that come off of our thunderstorms. We get a lot of those big thunder, lightning, and occasionally we do get hurricanes that are able to stay together enough on land that make it up our way. So again, lots of different weather, but this weather only happens in that troposphere, that lowest part of the atmosphere. Now, as you're looking up at the clouds, and I know California doesn't have a lot of clouds sometimes, so you have to look for them when you can. But when you look up in the sky and you're seeing these clouds, again, you're seeing ones that are lowest to you. That would be your cumulus and your stratus. Anytime you see nimbus, that means that there's moisture. Okay, that's the grayer clouds, a lot more water, and it's bringing rain. And then you've got higher clouds up in high altitude, those cirrus clouds, those mare's tails that are made more of those ice crystals and all. So again, we see the clouds again because of that rotational movement. And again, the changes in temperature and density. The clouds are a lot of fun. So here's a quick little poem that's maybe an easy way to remember some of these different types of clouds.
Clouds by Michael J. Dougherty, animated by Doris Rea and Hagos Tewaldi, read by Phoebe Chen. Cumulus clouds fly puffy and white. Some look like cotton balls, fluffy and light. The nimbus clouds fly dark and low. When you see them, it means rain or snow. Cirrus clouds are the wispy ones, and they sure can fly, like icy mare's tails, high in the sky. Stratus clouds have a layered look, stacking clouds as if a book. Fog is the lowest cloud you see, maybe a cloud that got caught in a tree. We thank Luke Howard for their name. Cloud identification is an easy game. The end.
Okay, so that may help you try to remember some of the clouds that we see. Now, particularly in the San Francisco Bay Area, you may recognize this as you're looking from the East Bay over towards the ocean. You see how those clouds are kind of rolling and folding over those Santa Cruz Mountains. Okay, what's happening there? Think about the motion that's going on. So the cold, dense air hits the Santa Cruz Mountains, and what happens to it? Is it gets kind of stuck until enough pressure builds behind that it pushes it. And again, it's heavier, dense air, so it's going to stay close to the ground. That's why it kind of flows over. Kind of an unusual phenomenon. Now, if you look at the bridge here, the San Francisco Bay Bridge, again, you see a little bit of the hill sticking out behind it. So how is it that you have these clouds that are sinking along the ground? That's again fog. It's just a lower cloud. Again, it's heavy and dense. Different temperatures and winds. They're just low-lying clouds. All right. Now, our atmospheric river in California, we talked a little bit about this with the oceans, about how your ocean water comes down from Alaska and it's cold water. Your atmospheric river in California is bringing a lot of moisture from that Pacific Ocean. And as you watch it spin here, can you find where you are in the Bay Area? Now, Oregon and Washington get a lot of rain. Bay Area, not so much. Southern California, not so much. So you can see again how these wind patterns are going to be determined by motion and the temperature of the oceans. All right, now this year especially, we've had a big adventure with weather. I don't know if any of you guys got out. This is Alameda. It was really cleared out all of vegetation, pushed down by all the floodwater. again, look at the size of the tree in the middle. So that was floated down from way upstream. And look at how the color of the water, see, it's very brown. It's got a lot of sediment in it because the water is moving so fast. It's strong enough to pick up a lot of those particles and carry it with them. So again, we have had a big boost of some weather lately. So again, just to review, as we look at this little Earth spinning, remember under the oceans, we do have the lithosphere base, and that does have the crust that's moving. It's got a lot of pressures on it as our planet rotates and revolves. We've got the internal heat that's coming from the core of our planet. Now, again, we've got that motion that's affecting our ocean, the way it moves and its currents. Those same motions affect the atmosphere and its currents. Now, when our ocean and our atmosphere work together, that's where we create our weather. All right. That is the end of the class today.